Hello everyone, I hope you're doing well. In this video, we are going to discuss topic which names as the distribution of speeds of particles in a classical gas. This topic is specifically from the chapter 7 of Introduction to Statistical Mechanics by Roger Bowley. This is a requested video. One of my students requested me to upload that lecture. Okay, so we are doing it now. If you have any question at the end of this video, you can ask me in comment section or simply email me. The email address is mentioned in the about section of my channel. So yeah, you are all welcome for any kinds of queries. And yeah, let's start the video. This topic is specifically related to the Maxwell distribution of molecular speeds for classical particles. When we talk about classical particles, here we are targeting classical gas. Okay, so our system under study is classical gas, and in this topic we'll target to find out an expression for the distribution function. Okay, the main thing that we will be doing here is to find out distribution function for our classical particles. Okay, for our system of classical particles, classical gas. The chapter itself names as the Maxwell distribution of speeds, maybe. Okay, and the chapter is typically targeting the distribution functions for that describes how the speeds and energies or wave vectors are distributed among a bunch of particles that are enclosed in a volume V, for example. Okay, so what does distribution mean? It's something like you can understand this concept of distribution by this anomaly. Like, for example, if your father have a property, okay, and there are 5 members in which among which this property has to be distributed. Okay, and let's say the property is not gonna be distributed equally to 5 of you. Some of you may get more of it and some of you may get less of it. What thing will decide that what kind of portion you'll get? Okay, each of member will get this thing will be determined by the distribution function. Okay, this distribution function will tell you that how the property will be distributed among the 5 members. Okay, similarly here the distribution of speeds of particle in a classical gas means that if you have a bunch of particles enclosed in a volume V, for example, okay, and in place of property, here property means money and the wealth, all of that. Here for a classical particle we have some classical properties. We have some properties not classical, just properties, for example speed and energy. So we want to know that how the speeds are distributed among those particles. Some of the particles will have greater speed, some of them will have smaller speed, and some of them will have very small speed, and some of them will have very larger speed. Some of them will have more speeds nearer to some mid value or something like that. How this speed distribution would look like. Okay, how the speeds would be distributed among particles, for example. This is something that we want to know, and this is something that we'll get at the end. And this is the distribution function that will tell us that most of the particle, for example, have speeds at this range, and a smaller number of particles have speeds in this range, and hence smaller number of particles will have speeds in the higher range as well. So the distribution function gives you a map of how the speeds you can replace the word speeds by property in order to visualize the concept even better, because mostly students don't understand this. It's like how much money will be distributed among all of the gas particles. So let me draw it here in clear form. Okay, let's say in x-axis we have money. Okay, like it's zero money, it's 0 rupees or dollars, for example, $1, $2, $3, $4, $5, and it is increasing to infinity right here. Okay, this is x-axis that shows money, and you can replace it with speed equivalently of particles. All right, I'm using this money analogy because this is something that we can easily understand, and after replacing money with speed you can easily understand what distribution function tells us. So here is the number density, for example, the number of particles that will have that money, and we can see that this is the peak. Okay, this shows that there are the maximum number of particles that have that the maximum number of members will get this money, will have this money distribution. For example, they will have $3. Most of the members, let's say, will get $3 as property, okay, and less of them will get the higher money. And you can see what number of particles will get what amount of money, and you can replace it with the concept that what number of particles will have which speed, okay, or which energy they would have. And yeah, that gives you a map of if you have so many particles here, what is their status, what is their status, what is their energy status, what most number of particles have. The most number of particles have $3, for example, or 3 meters per second speed, okay. You can easily know that what most of the particles inside that volume V have speed, okay, what energies they most probably have, or any other information could be extracted from that distribution function. That distribution function helps us to find out the average speeds, average wave vector, average energy the a bunch of particles have in a volume V, okay. So it gives quite a lot of data to us if we know the expression of it, okay. So what we'll do in this video is to find out the expression for the distribution function, okay, and let's start it. Okay, let's properly start it. I hope you now know what the distribution function is. That distribution function is very important, and that distribution function is equivalent to saying the wave function, the probability function that we usually take, that gives us the similar information, that carries all the information about the system, that wave function, okay. And if we take the square conjugate of it, it gives the probability density function, and that probability density function to the same task acts as the same beneficial quantity as the distribution function does in classical mechanics as well, okay. So yeah, now I'll properly I'll properly start that topic, and I'll not add this side informations anymore. We'll now focus on what's mentioned in the book and how the derivations are done, okay. So yeah, let we have a single particle, let a particle of mass m, okay, and let the probability that a particle will occupy a state defined by a state is defined by its wave function or its energy, okay. So let's call that wave function as psi I, okay, and with energy whose associated energy is EI, okay. For example, there is a state psi I, okay, and energy corresponding to that state is EI. So if you talk about psi I or EI, that means the same thing, okay. What we are doing is we want to find out the distribution function for a bunch of particles, but first we'll consider a single particle, and gradually we'll move towards the case that we are targeting. So first we'll talk about a single particle. Let's say we have a single particle like that, and we have bunch of energy states available, okay, and we want to find out the probability that what is the probability that each of these states will be occupied by this particle, by this single particle, okay. So that probability is given by the probability distribution function, Boltzmann distribution function, okay. Boltzmann probability distribution function gives us the probability that a particle will occupy a single particle state of energy EI, okay, and that expression is, let's say, P, okay, and I'm writing a small k here, okay, in small bracket, that shows the probability is function of k, which is the wave vector, that is given by e to the power minus e which is a function of k vector, okay, divided by kbt. Kb is Boltzmann constant, T is temperature, divided by Z, which is partition function. Okay, this probability distribution function, this Boltzmann distribution function, gives us the probability that a single particle will occupy the energy state. Let's write E. I. It's optional to write I or not. Okay, it's optional totally. You can even write E right here or something like that. It's totally optional. Write I here or not, that doesn't matter. So this is the probability that a single particle occupy that energy state. Now let's say we have so many of particles, okay, so many particles. Let's say we have so many particles here, and we want to find out the probability that that energy state will be occupied by one of these particles. Okay, where is the probability that this particle will occupy this? Where is the probability? Because there are so many particles, the probability function changes. Okay, the probability value changes, and that probability value, let's say we have, let we have capital N number of particles. Now the probability that one of these particles will occupy the energy state E is given by, the probability is simply given by the product. We are writing it with small n as a function of k, that is equals to capital N multiplied by the probability that a single particle will occupy that state. Okay, if we put value of p of k, which is e to the power minus e by kbt divided by z, you can write e of k, write that like that. Okay, I'm not writing it here to avoid, in order to avoid confusions. Okay, so that you may not confuse it as a real quantity being multiplied by e, but it's not, it's just showing that e would be a function of k here. So that is the probability that one of these particles will occupy that energy state, given that this value is very small. Okay, we are using here the classical approximation such that this expression gives us the probability, provided that probability is very small, that it approaches to 0, for example, means n of k is very small, and under that approximation, if you use some other methods, you can see that under that approximation where this expression approaches to 0, this expression gives us the average number of particles in an energy state E. That, for example, we have an energy state E and we have a bunch of particles, and since they are classical particles, there is no restriction on how much number of particles will occupy this state. For example, there may be 5 particles that can be at this energy state, and maybe 3 at this energy state and 4 at this energy state. So it's like how much number of particles or at single particles, and we here are talking about the average number of particles in E state. So on average, in a energy state, let's say E, how much number of particles will occupy in energy state E, that is something that we are talking. And that if that approximation holds, this number, this probability gives us the average number of particles. N of k gives us the average number of particles. There is another meaning that can be given to this expression under that approximation, under that classical approximation, that this expression mathematically would equal to the average number of particles in a energy state E. Okay, if you separately find out the expression for the average number of particle in energy state E and put that approximation on it, you will get this expression. This is another way to say it. Okay, these two expressions gets equal to each other under that approximation. So this gives us the average number of particles in an energy state E. Now we want to find out that how many number of particles. We were talking about here the absolute value of E. Okay, now we want to introduce some differentials. We want to introduce some range. Okay, for example, we have that range of energy like 3.5 to 4, and we want to find out that how many average number of on average. We are typically talking about average because more or less there is a difference in energy of each particle. Okay, and we are just talking about average values here when we have dispersed or variable data. So let's say we have these two energy values 3.5 and 4, and there are a ton of other values that lie between these two, 3.55, 3.51, 3.52, 3.53, and there are infinite number of values that lie between 3.5 and 4. So there are so many energy values here, and we want to find out that how much number of particles lie in this energy range. Okay, it's such that we are purchasing some clothes. Okay, in this range we or consider $3.5 to $4, and we want to find out in a store that how much clothes are there that lie in this range, in this price range. This is similar, this is analogy. Okay, so here now we want to find out the average number of particles that lie in the decay interval. Okay, that decay interval can be written as k and k plus dk, and these are two values, and if you subtract both of these values you will get the interval value. For example, if you subtract 4 by 3.5 you will get 0.5, so the range is 0.5. range means difference. Okay, so if you find the difference of these two values, k plus dk minus k, you will get dk. So dk is the range, while these are the absolute closing values, starter end point. Okay, so we want to find out the average number of particles that lie in this wave vector interval. Okay, k and k plus dk. So proceed, we can write n of k, that gives us the average number of particles in state E of k. All right, now we want to find out the average number of particles that have wave vectors in range k and k plus dk. Okay, we want to find out the average number of particles that have wave vectors k and k plus dk, and provided d of k is the density of states. Density of states gives us the number of states that are available to be occupied. Since there are not infinite number of states available to the particles to occupy, so for a system of particle to occupy, because it is very sensitive to the system you are considering, density of states accounts for that fact. Okay, so what we will do is to the average number of particles in the decay interval will be given by the product of average number of particle in state ek, okay, multiplied by d of k into dk. d of k dk, this product gives us the density of states that are available to be occupied for a system of classical gas. Okay, and n of k gives us the average number of particles that can occupy the state E of k. So the product will give us the number of particles that lie in the wave vector interval k plus k and k plus dk, such that d of k is the available number of states for the system of classical gas. And here we can put the value of n of k, which was actually n, probability function, which was e to the power minus e of k by kbt divided by z. D of k remains the same, and dk. Okay, here n is the number of particles, z is the partition function, d of k and dk. Now here let us call it as equation number 1. Here z is the partition function, and d of k are the density of states. Okay, now if we consider a free particle of mass m in a volume v, 3D case. Okay, then we know that the density of states for 3D system is given by this expression v k square by 2 pi square. Okay, for any 3D system, the density of states expression would be given by this formula, where v is the volume of the system, k is the k wave vector, pi is actually 3.14, which is a constant. And besides that, we have already derived, we have another thing here, which is partition function for a free particle in 3D. And if we consider the classical approximations as well, we have already derived the partition function for a particle in a three-dimensional box. Okay, for a free particle in three-dimensional box, which shows the particle in a 3D volume v. Okay, so for the partition function for that system is v by lambda d cube. Okay, this is the formula for the partition function for a free particle in 3D volume. And under classical approximation, we have did this, and I'll link that video in the comment section. You can check out its proof if you want. So you can visit chapter 5. Okay, and this is equation number 5.9.6. you can visit it to have some reference. This is the direct result that we'll put here, because its derivation is not relevant right there. It requires another video, and I have already uploaded that video, so I'll link it simply. So we'll put both of these values for a free particle in 3D volume under classical approximation. So we'll put both of these values right into this expression to get some simplification. And f of k dk equals n e to the power minus e of k by kbt divided by z. In place of z, we'll write v divided by lambda d cube. Lambda d is actually the de Broglie wavelength. Okay, it has some certain expression, and I write it after that. If you want some clean notes, so I have also started to make notes, and I sell them in cheap values. For example, they will be more or less $2 each. Okay, so when they are ready, I'll link all of those right in the comment section or in description box. You can check them out. If you want some clean and detailed notes on different topics, then you can check them out. You can buy them, and yeah, that's the kind of service that I'm planning to give you all people, because I know that notes are crucial for exam preparation, and sometimes you don't have a time to watch the video, and you have to just go through you just need to go through those notes, and you'll understand it. I'll make them crystal clear for you people. So yeah, let us simplify it. This volume v and this volume v just gets cancelled out, and we are left with n. This lambda d cube is in the denominator of a denominator, so it comes right here in the numerator. So n lambda d cube, this d is in the subscript, it's not actually a thing. Okay, so this remains the same, k square and 2 pi square here dk. Okay, this is the probability distribution function so far in terms of wave vector. Okay, now let us convert it into speeds term, because we want to find out the molecular distribution of speeds. Okay, Maxwell distribution of speeds formula needs to be determined. That is why we will convert from k to u space. We will represent speed by u symbol. Okay, now let us first write the value of lambda d, which is 2 pi h square by m kbt, and whole power is 1 by 2, and it is called as the thermal de Broglie wavelength. This is introduced in the same topic where we have proved this formula. Okay, it was taken as a useful constant, and we named it as thermal de Broglie wavelength, as it has those units of wavelength. That is why. And we can see here that in the final formula volume cancels out, and hence the volume of the original system doesn't matter, it becomes irrelevant. Now we want to consider a non-relativistic formula. We have, for a non-relativistic particle, for a relativistic particle, the formula and the treatment gets a little bit different. For non-relativistic particle, we know that P is equals to mv. Okay, I'm using v, no, u. Okay, u, I'm using u as speed. So we know that quantum mechanically P is equals to h cut k, so we'll write h cut k here. P is equals to h cut k is momentum expression in quantum mechanics, and P is equals to mu, you know, in classical mechanics. So yeah, relativistic effects, quantum effects, and classical effects, there are three categories. Okay, there are three different things, and we can have k is equals to mu by h cut here. Okay, this is the value of k. We'll simply put the value of k right into this expression. Okay, there is a little bit one more step to do, but yeah, let us call it as equation number 2. Okay, we want to convert it into u space, so f of u du would be simply equals to f of k dk by du du. Okay, you have to multiply it, this differential, in order to make that transformation from k space to u space. This is always done from when you are converting from a certain space to another space. So at this point some of you might get confused at how I have wrote this expression. So let me introduce to you one of the easiest way to write it. Okay, uh, because if you want to convert an expression from one space to another space, there are certain things that you have to do, and keep that in mind, that the product of distribution function, okay, let's say first we'll consider in k space with dk interval, this product will be equals to the product of distribution function in u space, which is speed space, multiplied by the du interval. And similarly, if you had been interested in the energy space, then similarly we'll have that distribution function in terms of energy multiplied by the dE interval. Okay, and similarly if you are considering the omega space, then the similar thing will hold as well. Okay, now since we are considering this two combinations, we are considering the k to u space thing, then let us have this expression right here. What we want to find out is this thing. Okay, and we have this thing in our question, so let us put the value of f of k and value of dk. Okay, that is calculated from the relation of k and u, which was, we know that mv equals h cut k, and mv by h cut would be equals to k. So we can find out the value of dk from here in terms of v, and we will simply plug that value right into this expression, and we will find out that whether we'll get the similar result or not. Okay, so this is the simplest thing that you can do. If that kind of differentiation and all that stuff confuses you, then you can use this method. This is equally valid. Okay, there is no problem in that. So yeah, that's totally up to you. There are two ways in which you can write this formula, and you choose your way. Okay, so we know the value of f of k. For value of dk, we can calculate it from here. We have m by h cut dv equals dk. I hope you people know that how to find out differentials. You can also do it by, we have that k is equals to m by h cut, which is constant, into v, differentiating with respect to v. Okay, so we'll get m by h cut dv by dv is 1, so that is why we will write it like that. This dv goes onto this side of equation, because what we want is the value of dk. So this is how you will get the value of dk, and you will put that value right into this expression, because you want to convert all of that expression into u space, and you want to eradicate all of k in this formula. Okay, you don't want to see k in your place here, so that is why we'll put this value of dk right into this expression, and you'll get the similar result. Let me show you it to you people. What is the value of f of k? Let me see. After I filmed the whole video, I just got that idea to write this perspective as well for some of you who wants to have this thing. So yeah, this is f of k dk, and this is the value of f of k, okay, other than dk, because we are not considering dk. We want to put the value of f of k, which is this whole thing. So let me put all the value right into this expression, expression to get what we want. So n lambda d cube, or should I pause and write it directly? E by kbt by 2 pi square k square. Okay, this is the value of f of k, and value of dk is m by h cut dv. And okay, and we have that e to the power, this is e, this is kinetic energy, and since we want to express the whole expression in terms of u, so we will put the value of kinetic energy in terms of velocity, which is 1/2 m u square. Okay, we'll put that value right into this expression, so it will become m u square in the numerator and 2 kbt in the denominator, because we know that 2 is in the denominator. So for k square, we know the value of k, which is mv by h cut. So let us put the value of k square, means the whole square of all these quantities, m square v square divided by h cut square, and this m by h cut as it is, and dv. Okay, after that let us simplify the whole things, and it will become m square, and m, it will become m cube divided by h cut cube, and we have e to the power minus m v square by 2 kbt and v square dv. This is the Maxwell distribution function. Okay, Maxwell distribution function of molecular speed. And yeah, that is something that we calculated for the other case as well. Okay, I'm adding this part just as an additional information, as an additional approach that you can have in order to convert from one space to another space. And here you can see all of these relations. You can easily convert them from one form to another form, so that you just need to know the value of energy in terms of k space, in terms of u space, in terms of e, it's simply e, in terms of omega space. You should know all of these formulas only, and you can easily convert from one space to another space. And f of u dv equals n lambda d cube, okay, divided by 2 pi square, and I have written these values now: m cube by h cut cube by h cut cube u square e to the power minus m u square by 2 kbt du. This is expression number 4. Let's say this is the Maxwell distribution of molecular speeds. This is the official formula in terms of speeds. Okay, Maxwell distribution of molecular speeds. And we can see here that this distribution is proportional to, there is a variable term here, this is the variable term, none of the other values are variable, but this, so it is proportional to u square. This is proportional to, this distribution is proportional to u square e to the power minus m u square 2 kbt. Okay, at large value of u, this function determines the distribution function. At smaller values, this determines the behavior of distribution function, and at moderate value, both of these blends to form the shape of distribution function. Okay, as we have derived an expression for distribution function of molecular speeds, which is Maxwell distribution of speeds of particles in three-dimensional system, okay, as written here. So we need to understand this graph as well, because it shows how the distribution looks like. Okay, if you put all of those values, and how you will get the map of the property that has been distributed among the gas molecules. So you can see here, this is the y-axis line. Okay, here this is the y-axis line, as you can see, and in y-axis we have that distribution function n of u, that tells us the number of particles that have that have speeds u. Okay, and in x-axis we have speed u. Okay, so this is the origin, let's say, and this is the 0 point. Okay, this point, or at origin we have 0 speed and 0 number of particles, and at we can see here how this graph is moving upward like that. And at lower speeds, as I told you before, the distribution is determined by the square function. Okay, if you put the limit of u approaches to 0, we'll say that the distribution function largely depends upon the u square function. So at very lower speeds, if you if you zoom it very much, then you will see that at lower speeds the distribution varies as the square. Okay, as the square of the speeds at the very lower speeds right here. Okay, and at higher values of speeds, you can see here like that, the distribution function is dictated by the exponential function. And at exponential function, this is the property of exponential functions, that at speeds, as the quantity, as the variable gets very large in the negative power of exponential, the whole exponential function decreases to become 0 at a very rapid rate. Okay, that decrement in the quantity occurs at very greater rate. It fastly reaches to 0 point, so it makes the distribution function reaches to 0 as the speed gets higher. This thing, if we talk about inverse, means that we have the, at y-axis we have average number of particles that have those speeds. So it means that very less number of particles have very higher speeds. Okay, it means very less number of particles will get property of large value. So yeah, and at lower speeds you can see that the quantity is less as well, but most of the particles lie in this region, which is the moderate region. Okay, the medium region, we can see there are very less particles which have energies or speeds, you can say, very less. Okay, that approaches to 0, and where there are very less number of particles as compared to these particles. There are very less number of particles that have very greater speeds, and most of the particles, most of the gas molecules that you have here will have speeds in this range. Okay, will have speeds in this range. We can see here that the value of n of u is greater for these ranges. Okay, from this point to this point, you can say, let's say this is u1 velocity, here there is u1 velocity, this is u2 velocity, and we can see that in the interval of u1 and u2 we have the most number of particles, as the value of n of u in this range is higher, while it gets lower for the rest of the graph. So I hope you understand what I'm saying here. The graph is, these are the value of n of u, you can see, and this is, let's say, if you calibrate it just in order to make you people understand, let's say it is 1 2 3 value, 4 5 and 6. Okay, it is increasing on the vertical direction, and they show the number of particles on those velocities. So you can see here that there are 6 particles, let's say, in this speed. Okay, there are 5 particles in this speed, 5 particles in this speed as well, 4 particles in this speed. And you can see for these speeds the particles are very lesser in number, while most of the particles, if you find out the sum, you will get that most of the particles have speeds in this range. And you can find out the total number of particles very easily. You can also dictate it by seeing that the area under this graph is the largest. Okay, if the area under the graph is largest, it means the quantity under study is maximum here. Okay, and you can see the area in the small the area here is very small. Okay, this area is very small as well, which shows that very less the number of particles are there. Okay, and it's maximum here. So yeah, this is the graph and how the distribution of speeds look like. In the medium range, in this range, this whole product of u square and the exponential term determines the shape of the graph, while in the greater velocity limit, exponential function dictates. In the smaller speeds limit, the squared function, the quadratic function dictates the shape of the graph. So yes, that is it for the shape of the graph. You should know it and draw it whenever the topic comes in. When you have to discuss the Maxwell distribution of speeds, do mention the graph and explain the various aspects of this graph as well. I hope you got some idea of how the graph looks like. And yes, you can talk about the lower speed limits, higher speed limits, and the moderate region where the most of the particles, where the functional distribution function is most populated. So yeah, these are the terms that you can use to describe this kind of graph. Yeah. um, This is the distribution function, and as we have found the distribution function, we can calculate rest of all the values very easily. For example, since we have distribution function now in terms of k and u as well, okay, function, we can calculate average values very easily. Average value of any physical property, of any physical quantity, for example, speed, energy, or else, okay, by using following general formula. Whenever you want to find out the average value of any quantity, you'll use this general formula. Simply you'll put these values, simplify it, and you'll get the average value. For example, we want to find out the average value of some a quantity, okay, which will be the general formula. It will be integral from 0 to infinity f of k, which will be the distribution function, or f of u. It depends what space you want to consider. So f of k multiplied by a of k. If you are considering k space, then this function will be in k space as well. All of them will be in same space. It depends which space you are considering. If it would have been u, so it will be u all over here. So 0 to infinity f of k dk. Simply this is the expression for the average value. And for example, if you want to find out the average value of speed is u, okay. So what you will do is f of I'm using u then here, okay, since it will be easy. F of u, then in place of a we will write u, because we want to find out the average value of u. A is the quantity whose average value needs to be calculated, so it's u here. So in place of a you write u, then in place of k dk you write du, and 0 to infinity f of u du, okay. Similarly, for average kinetic energy, it's optional whether to use k space or u space. I'll write it here the k space because we have already write it in u space. You know what will be the kinetic energy in u space, so I'm doing it for k space. F of k into kinetic energy term into dk divided by 0 to infinity f of k dk. And kinetic energy in k space, kinetic energy in k space for a free particle is h get square k square by 2m, okay. H get square by 2m just comes out of the integral, so it will be solved to find out the kinetic energy, the average kinetic energy. Similarly, if you want to find out the k square, average value of k square, average value of k, whatever you want to do, you can do it using this formula, okay. I'll do it for example for k and k square, because the similar one is done in the book, but the results were mentioned directly. And using these results, we can find out the average kinetic energy expression, average mean square velocity, okay, average speeds. We can find out all these values using this thing. And since you know that if you know the value of average k, for example, and you know this result, this relation, which is k is equals to mu by h cut, so average k will be equals to m by h cut average velocity. So if you know average velocity, you can find out average wave vector. If you know average wave vector, you can easily find out average velocity as well. So they are interchangeably related, and you can easily find them out from each other, okay, since they are all related to each other. Once you have calculated k square, you can calculate u square as well using this formula. If you know u square bar, then you can find out the mean square velocity, which is actually root mean square velocity. So if you take the under root of that mean of square of velocity, you will get root mean square of velocity. Okay, we'll derive all of these formulas in next video, because the video has gotten so much lengthy, and yeah, so we'll meet in next video. We'll derive all of these results, okay, because we have derived already the Maxwell distribution function, the main distribution function that was the, you know, the main guest of the video. So we have introduced it to you people. Let us do the rest of the things in next video. I hope you all enjoyed it, and if you have any queries, you can ask me. I'll link those parts in the comment section. You can easily check them out. If you want any specific video that you are finding it difficult to find in my channel, because there are a ton of videos on my channel, I have made separate playlist for you people to easily get to your video, but sometimes it gets difficult. You can just comment your topic in the comment means comment, okay. Just comment it, and I'll reply to you with the link of that video if it is already uploaded. Otherwise, I'll upload the video very soon for you people. Okay, so goodbye.